So then we'll talk about parameter inference and model error and the goals of calibration. So, you're looking forward to it, sir?
Yes, so thank you for having me once again. This is my third visit during this program, and I've got a few more. And in my last two talks, I gave something rather formal based on work I'd been doing with Victoria in the first instance, which is now submitted and on archive, and with James, ditto, in the second instance. And I planned in this talk to do something based on what I've been thinking about here. So I thought coming here would be a wonderful opportunity to start to try and flesh out some of those nagging thoughts that I have in the back of my mind when I just do the thing that I always do with my collaborators and so forth. And I have to say it's been a wonderfully stimulating environment talking to applied mathematicians who write the problem down in different ways and think about different things. It really challenges you to sort of be confident in your own views. So I ask you to forgive me somewhat for the informal nature of this talk. Yes, there are slides, but the maths isn't massively worked out. I haven't proved anything, but I have been thinking. So we're very much contrasting David's talk where you have years of collaboration and papers and two R packages, two in one talk. This is sort of, well, the complement of that set. Okay, so motivation. And I'm going to write the problem down in a way that will be challenging both for the statisticians and for the applied mathematicians, just so I can bring the community together in sort of what the hell is he going on about type ways. So we'll have some physical process, Y. Now throughout the talk I'll be thinking of Y as kind of climate, so climate models will be the example. And there's a nice middle section of the talk where I explain what climate models are, what their genesis is, and what people do with them. But I want to set the problem up mathematically a little bit first. So we're going to take some observations of the truth with some error. And those observations will be some incidence matrix times the process. So what's that H? Well, the process, maybe climate's evolving in time and it's going to carry on for quite a long time, we hope. We're not going to observe it in 2080 and so forth. We just observed it now. So your H is sort of ones and zeros that indicate where you've observed it and where you haven't. And this W will be a sort of white noise process, measurement error. Nothing so fancy yet. And I have a model, a computer simulator for Y, F, that some is telling me something about F, apparently. And there are some parameters in this model. And the usual UQ questions are, well, how does F inform me about the process? And what should the parameters be? So I'm talking about an inverse problem. I'm probably going a bit slowly. Now in statistics, and I believe UQ more generally, our approach, so our model as a mathematical community, looks a bit like this. We make what Kennedy and O'Hagan called a best input assumption, where we say that the process, the real thing, is our model at some true parameter values. I'm calling these X star, and I'm sorry to the applied mathematicians who think X should be space, but I get lost when I talk about it as not a parameter, so please just bear with that. And then there's this structural error term, which in the model, and this is crucial, is independent of those parameters and of the model. So it's this process that sits outside. And we have Bayesian methods where you put some prior on what this truth is, this true parameter, and then you can get a posteriori by updating the data and model runs. And we heard about history matching, where you basically cut out the parameter space that doesn't have this best input. So all of our approaches to inverse problems start with, there is one, and we're looking for it. What is it? And then we do stuff. So do we actually think that this X star exists? Like, if we're going to do parameter inference, is it important that we ascribe some physical meaning to the parameters when we get to the end? Is there a true best input? Do the modelers think that? I mean, that's kind of crucial. We tell them, your model F has discrepancy. This is what statisticians tell them anyway. but this is our model, and I don't think we often tell them that it might be wrong, if indeed it is. If we think there is an existence of X star, what does it mean? And you would be surprised to think that many people within our communities think it means different things. And then the ultimate question that I would love to solve is, how do we get at this discrepancy variance term? How wrong is the model? Now I must say quickly that what Angela was doing is completely fine in this instance. So if you're just interested in this sum, that's fine, that's identifiable. So whether it's ascribed to the model or the discrepancy, once you adjust by the data, you're okay if you're sort of doing interpolation type prediction. But if you're interested in what X star is for some reason, then maybe what I've got to say will be a bit interesting. So I'm going to try and go through some of the things that people think about. We had this nice paper by Brynjarsdottir and O'Hagan a few years ago, where they showed what happens if you ignore model discrepancy for parameter inference. And this is their figure, so theta star is our X star here. So it doesn't matter how many observations of the real that you take, if you ignore discrepancy, you miss it and you over-concentrate. So this is well known in sort of Bayesian modeling, where you have a model misspecification, you just become very confident about the wrong thing. And they also showed that if you just put a sort of non-informative prior something fluid, then you often miss what the true values of the parameters are, and you need to do something a bit cleverer and putting more structure into the prior if you really want to do inference. Now, they still show in that paper that if you want to do prediction of, you know, the truth, that's okay, because it doesn't really matter in some situations, perhaps this engineering example we saw this morning, whether your model is the physical model, or your signal's coming from the physical model, or if it's coming from the physical model plus the stochastic process. Maybe it doesn't matter. In climate, I'm going to try and argue that it will matter, and so we probably do care about this in some sense. So, some other ideas. Wong and those guys last year published a paper that said, well, actually this best input thing isn't what Kennedy and O'Hagan said it was, which was best in some regression sense. It's best in that it gives you the model that is nearest to the truth. So you have a situation where here's the space of things that my model can do over here, and here are my observations, and I'm going to define X star to be the closest point to this set, which is a thing that you can do, but perhaps parameter inference for that loses some sort of physical meaning. By the way, I should say, of course, Kennedy and O'Hagan talked at length in that paper about not ascribing physical meaning to those parameters. So in our first talk, if you had one of your parameters was the mass of a black hole, your inference for that parameter doesn't mean anything about the mass of the actual black hole unless you decide that it does, but that's something you added at the end. Then there's the rarefied stuff, which says, well, we only like this best input assumption for some theoretical model. Think of the theoretical model almost like the infinite solution to the PDE plus some stuff that we thought to add in, sort of if we could improve the physics and the discretization and so forth. And then our current model sits below it somewhere in a hierarchy, and then you have to do some work to try and figure out your way up to the top. And then there's this paper by Plumley where you impose orthogonality as well on the discrepancy, and you get some form of identifiability. And some of the things I was talking about in my last talk about sort of delaying the Bayesian update in some sense until you've started to see how bad your model is. Okay, so whether you agreed with that survey of what X star is, and whether you're thinking, oh God, it's just this thing, you know, I have a prior measure, I've got a posterior, go away, fine. You can forget all of that and just think about climate models for a few minutes. Maybe I'll say something interesting about what they are. So climate models are essentially simulators that solve Navier-Stokes on the rotating sphere. But that's pretty hard to do, and so you have to discretize your solution. in some sense. And when you discretize and you start to solve it, you have developed what's called the dynamical core for a climate model. And that doesn't resolve basically any process that's super interesting, like what clouds are doing and what ocean currents are doing and what convection is doing. So you have to put those things in, and putting those things in forms what's called the physics package of the climate model. So you have a big PDE solved dynamically, and then at every time step you do some gubbins. So sometimes that's an ODE, sometimes it's a linearized PDE, sometimes it's just some regression or something that's trying to fit the curve profile to something else. So I observe that temperature and water does this when it goes from one part of space to another, so I try and fit a regression to do that. And there are millions of lines of code, and there are if statements, and who knows. So it's almost like a black box with some physics in it. And so each center in the world has one of these things and is working pretty hard on developing the next one right now, because the deadline for submitting one of these is coming up. So the UK has one, America has two, of course. Germany, France, everywhere has one. And they submit them in a sequence of organized experiments called coupled model into comparison projects. So these are the outputs for phase 5. And these outputs, it takes them about 8 years to figure out what the configuration of the model is going to be and run it. And the coupled model into comparison gives you a bunch of forcings you have to do. So you have to go through history, and then you have to do CO2 at some level into the future and some different levels to explore what's going on. And then each of these runs is a climate model. So it's a country's endeavor for 8 years is one of these small lines. Okay, and then these things are used by basically everybody to get uncertainty on all kinds of complex systems, some of which you might be working in. So let's just look at that workflow. Physics and process-based understanding, plus the biggest computers we have on the planet and state-of-the-art numerics, plus some of the coolest observations around, and I really mean this, everything from, yes, we have satellites and ships, but the little floats that live 1,000 meters below the sea, we just dumped a load of these guys in, and they womble around the world's oceans under their own volition, not doing anything, just letting the currents take them. And then every 10 days they go, oh, I'm going to go down, take a big measurement, beam it up to a satellite, and then go back to my sort of global swim. And you can follow their positions in pictures of little icons of little ducks swimming around the planet if you want. There's a website for that. They fit stuff to seals and whales, and they swim about under the ice and give us all sorts of cool measurements. And then how you turn those into data is just fantastic stuff. And then there's all of these. This is what your experiment has to do. And that feeds into modeling at this handful of centers where they develop this sort of physics plus engineering plus computer science stuff. And then that feeds into maybe some weather forecasting stuff and into these single integrations I told you about. And then almost all climate papers are just taking these single integrations and looking for signals and mechanisms and things that are common across the models, so that ultimately you can feed back up to here for the next round. We care about what's going to happen into the future so that we can make policy, and people use idealized models that are sort of maybe the last generation or the two before of that. And then you get all of your decisions and decision support. Now there's a lot of UQ done from this set of runs to the future. There's some on idealized models. We don't have anything yet going from the global models to give you the true model, but you can see why you might want to. So this is some of the stuff that I've worked on, trying to go down here, but there won't be anything in the next phase from my stuff, I don't think. So you tune your climate model. It spits out hundreds of fields in time that look like this. So the data, they take the output, this is temperature, minus the observations, and then they color it so that white, they don't care, red, it's too warm and they want to get rid of it, blue, it's too cold and they want to get rid of it. And they look at this across all kinds of different outputs and try to change the model parameters to get rid of some of the worst blobs, like this one for the Canadian model over North America. The heat is sort of worrying. So it's like a calibration problem. Fine. Now, statistical attempts to take those single integrations from all the modeling centers don't use any traditional UQ. They take the runs as if we don't know anything about the parameters or how they were arrived at, and make a series of exchangeability assumptions. So every serious attempt I know does something that can be boiled down to this model. And what you say is that each of these climate models, one from each center, are exchangeable, or second order exchangeable. So what does exchangeable mean? It's like the weakest assumption we could possibly make. It says that before I see the data, if you're asking me the mean and variance of the UK model, I don't have any feelings for how that is different from the US model or the Canadian model. So a priori, of course it will be different after we see it. So that's exchangeability across models, and if you want to be fully probabilistic, you can say the distributions are the same right now, according to me. And then they make this relationship with y is consistent too. So I have no reason to think the UK's model is closer to real than the Americans' model is closer to real. And that's all they say. And from that, a set of theorems give you a statistical model for free. The fully probabilistic version of this is due to Definetti. This is due to Michael Goldstein in the 80s. I think it was the 80s. So you say every model must have, therefore, a common mean plus some mean zero stuff with a variance. And this relationship says, well, therefore, if they all have the same covariance, there must be a piece of this common mean in there, and then, again, discrepancy comes up. So this is the model for treating all of the different climate models that come in this sort of God-given, well, God, I mean, the modeling centers are God here, but they might as well be. This is our model for relating that to reality. Okay, so I'm very interested in like unifying frameworks because we think of things in terms of the parameters. Okay, so I think this is a contentious model. So we're on to the new thought again. And moreover, the climate modelers that I work with really don't like it. They really don't like it. It's one of those things where we maybe spend the first half a day arguing why there should be one true model. Because after all, this model means that if I could find that best input and run the climate model, I'd be happy to throw it away, and everything else is just that difference. Well, they don't buy that. They've seen their model too many times. They know that over here it's good at temperature, over here it's good at precip, and I might learn something about reality by seeing how these things differ over the physics. Now, Michael's model, the rarefied model, does somehow make sense of that, but not in a way that I know how to actually do for climate. So instead, I'd like to propose a different kind of inference. Maybe we care about a set. So I want to say, I don't think there is a best input. I think there's a set of models that I'm interested in, which is why I love David's talk, because he's going to find it for me. Okay, so there's some set I'm interested in. I have to define this set, of course, but the models inside the set are informative for reality, and the models outside of the set are not. That's my proposition. By the way, this is thoughts at this program, so please feel free to help me get this into something better if you don't like it. Okay, so let this tetras bar function, I love tetras, be the indicator that I'm in this set, okay, a natural function. And let's suppose I have a sequence of parameter values where this tetras function is 1. Then my judgment is going to be that inside this set, I have this exchangeability. So I'm indifferent over those labels in this set. And we can argue about whether that's a good assumption or not, because we always think of Gaussian processes, and therefore that wouldn't be true. But I'm imagining the set is a pretty small subset of the original parameter space, so that right now I can't tell you much different about different runs in that space and how they might be different. So if I am allowed to assume that these are some exchangeable sequence, and then I say that reality has the same relationship between every member before I've seen any member, then I get myself a new model for free. So this isn't best input anymore. So I have a new model for all of my models that says there's some model mean. Note this might not be a realization of the function. No reason it should be. And then my reality is somehow correlated with it. Now, before you hate me forever, let me give you 2 reasons why I like this model. First, well, 3 reasons. The first is it's simple. I mean, it's the simplest judgment I can make, even if you disagree with it. The first real reason is that the extension allows the unification of those 2 frameworks in climate. So I can say that my particular climate model, this one, has some representation, and there's an underlying model mean for my climate model with some residual. And then if I make the same exchangeability over the representations for the different models, I get a framework that I can do inference on very easily. And I stop this sub-communities of people taking all of this UQ, if we were to do any, and then pretending they didn't know anything. The second answers the climate modeler's main objection, which is, well, over here temperature's good, over here precipitation's good, and I don't want to rule any of them out. I feel like there's something going on in both. Well, I can capture that very easily. I can say, well, okay, my set is the union of 2 disjoint sets, and there is a correlation between models in this set for these types of outputs, and a correlation between parts of this set for those types of outputs, and this is a sort of suggestive way of handling that. And the mathematics works out just fine. Okay, so that's why I like it. So, instead of looking for a posterior distribution over X star, or a set that isn't the best input, as in history matching, I'm looking for the set of models where I'm prepared to make this exchangeability judgment. So it's a different thing. But it's got a lot of the same features, right? I'm not getting rid of discrepancy, I'm just changing its definition, and now it's still this big elephant in the room that I have to solve. And now I have to solve when am I in this set and when am I not, and how do I define it? Okay, so quickly beginning with the case where we know the discrepancy. So this is the slide that I would like to use to define history matching. This is history matching under the best input, by the way. So you define a distance, a Mahalanobis distance, between your observations and your model, and the distance is under the variance norm, or the covariance inner product in the Hilbert space. Fine. So in the case that you're using a GP emulator, it looks like that, and for the best input model, that variance has this expression that Peter showed on his slide. Okay, well, in our model, that distance, I can still define a Mahalanobis distance under the variance norm, but now I have a different model, so it turns out I have a different norm. And these are distance between the models, assuming that I'm in my set or not. And I'm going to use this distance to say, well, if it's big, then I'm not in my set. So I'm going to define my set as values where this distance exceeds a threshold. So we're moving into David's talk. And you can easily show, I guess, that if you consider these differences to be roughly normal, then the distances should have a chi-squared distribution with this non-centrality parameter. So you can get some idea of what this threshold should be if you were in this set or not, but that's an aside. Okay, so most of these are pictures, by the way, so don't worry. Lunch is coming. So the idea is to start with this tolerance to error type discrepancy that Peter was talking about. I get this for free from the climate modelers because they give me these color plots and they have white on them, and white has a temperature range or some other range, and that tells me what they don't care about. So they would like to make the whole picture white. Does the model make it white? No, but we'll start with hoping that it can, and we'll use history matching, or we'll abuse it, in fact, to cut down as much space we can as possible. Just cut out 90% at a time, reiterate, and find the set of models that are in some sense closest under this tolerance to error, and then we'll do something. Okay, so far no analysis. And we're going to look at the convergence of this minimum distance and then use this to set model discrepancy. Okay, so let's do this in an example. Okay, so back to reality slightly. I showed a version of this test problem in my last talk. We have a 10 by 10 spatial field model, so it outputs these 10 by 10 grids, and it's got 6 inputs. And when we ran it a lot, this I think about 60 times, you get a mean that looks like this. So it's got an off-diagonal signal. And this is back from our ocean modeling days, where we were trying to set up a test problem that said, okay, the ocean model has the Gulf Stream in the wrong bloody place all the time. Do we have methodology capable of finding out if the Gulf Stream really could lie in the right place? So in this model, the right place does exist. It's about 0.4% of parameter space, but most of the time it's in the wrong place. And so you're trying to test whether you can find signals that look like this. Now, here's a sort of sample of the first set of runs, and you can see you always get this kind of off-diagonal signal, and you don't get the clean diagonal signal. To make it harder than the problem I showed last time, I decided that there was going to be a blob of stuff that we could never do. Okay, so the model can't get this blob of stuff that we're going to see in the observation. So I have some discrepancy with there's a blob down here. So I'm now going to take, I've got some observations, I've got a model that always has an off-diagonal signal. I don't know whether it can do the diagonal signal or not, and I don't know if it can do this blob or not, and I'm going to play this game of getting as close as possible and trying to figure out discrepancy via something. Okay, so how would you do that? Well, the protocol will be run the model, find the distance for all the runs. In fact, you can emulate the distance, which we do here, but you could emulate the function and work out the distances either way. And just zoom in and see if this is going to start to work in some sense. So we do that. You cut out 90% of the space and you run the model again, and lo and behold, it's still all bad. Okay? And then we do it again, and the signal starts to pop out. This is just purely distance close to the model. I haven't got an informed discrepancy yet. And you iterate and you get closer, and you start to see more and more of your models have this diagonal signal, but there's no blob. Okay, the blob is missing. Okay, fine. And after about 6 waves, you start to be sure that the blob's not going to be there anymore because everything seems to be constant. Indeed, convergence happens, and this would be the traditional bound that we would use in history matching that cut out all the space. So you get this idea that, no, the model can't reproduce everything, but it's seeming to get things that are quite close in terms of this diagonal. So how would I infer discrepancy? Well, I'm going to sort of do something like what Andrew was talking about. Discrepancy has to come from the modeler, and I think every talk that we see that will address discrepancy will admit to that. It's outside of the model. But in some sense, they're asking me what the discrepancy is. So we have to sort of get a two-way conversation about it going. And the best way to get a two-way conversation with a modeler going is to start running their model and playing with them. And that's my idea here. So we have a bunch of runs from this telescoping thing, and we can start to look at all of the runs that are close and say, okay, well, bad news, I'm afraid we're not going to get everything that you wanted. This blob's not going away. But which of these runs that we've done would be close enough, given this not working? And so you can go through and pick out all of the runs that don't have much on the diagonal and stuff, and effectively do what Andrew was doing, like label them. Yes, this is in, no, this is out. And that would be a human-in-the-loop step that is now going to give you some information from which you can model your discrepancy. So I did that here, and finally you can, just by looking at the variance of these runs and the difference, you can then get an actual inference under the model I wrote down a few slides ago that gives you a discrepancy that has the blob and a sort of prediction that has both features in it. Okay, so that's like an early work calculation to prove you can do something, but it's not anything finished. So yeah, to sum up, I don't think we have to assume there is one true input. I think it's a useful tool. Perhaps there are other ways, especially if the modelers don't like it. Please argue with me over lunch or over tomorrow's lunch. Thank you.
Okay, thank you, Demi. Are there any questions for Demi?
Yeah, so the struggle with all of this modelling is what comes from the model, what is the difference between the model and the world, and what is the relationship between the difference and the model signal. So I was trying to follow in your analysis, so the way you set it up, okay, which seems interesting to me. I mean, so you get an average, there's a mean in the set that you include of model runs, yep. There is a co-exchangeability with real, yep. So therefore, there's a sharing of means, and everything else is, the extra bits are uncorrelated, yep. Okay. So that's the part that I find, that I struggle with, because, I mean, the whole reason I moved over to the rarefied form was because I couldn't accept that lack of correlation. And so my comment on that is that probably you want to say, yeah, I know I said that, but I still want to build the correlation back in. Because if you just think about the values of the quantities, I mean, so the question is the information in the values, the f of x's, or is it in the form of the f? Because the extent to which there's information in the form of the f, yeah, that you know that form of the f is like, but not exactly the same as, if you modelled it more carefully. There's an intrinsic correlation that you're kind of missing in doing that. We should talk about that more.
Yeah,
but,
I'll have to think about that.
Yeah. The thing when I think you said that you kind of verification magically makes it work, but you can't do it. I mean, it points to the correlations that you need to think about.
Yeah. Hi.
This will be a very naive question. So you're using Navier-Stokes and you're doing time stepping and you're sticking in parameters. How do you determine the parameters at each succeeding time step? Is that done independent of the model that you had set up for? Are there separate models for the parameters? How is that done?
Yeah, so
I don't know.
obviously I don't solve Navier-Stokes or do climate modeling, but yes, exactly. So usually the parameters are static, and they just feed in every time step. So there's a physics package essentially that the dynamics calls at every time step and say, okay, here's what I want to do with the integration in terms of moving fluids and traces around grid boxes. What else do I need to do? And that physics package will sort of shift all of those things around according to the equations for different parts of it. But we're talking about coupled models where there's stuff telling the ocean how to mix on the boundaries, there's stuff telling how the air should convect up a column so that you have clouds, and all sorts of other stuff in between. I mean, this is millions of lines of code. No one person writes this thing.
That's what I'm trying to understand, the general principle.
Yeah.
Do they use the given run? So you do a run and you get some computation at a new time step. Now, do they take that computation at the new time step to determine the new set of parameters to set into?
They don't know. The parameters aren't determined online. They're just, you can run it for a fixed set of the parameters and that's it.
But are the parameters changing with the time steps?
No, there's been some work in simpler models to try and do a sort of data assimilation type thing where you add the parameters to the state vector and then you do that kind of thing that we're used to in data assimilation and try and update them. But there are papers saying why it doesn't work, whether it does or not.
At the end, you have this human in the loop bit where you show the modelers some results and they say, I like those and I don't like those. But you can only show them a finite number, probably a fairly small finite number given their patience and such like.
Quite.
So how are you going to get a guarantee that you've found your set, or not just a subset for your set?
Well, so I have, this is a good design problem, right? So I'm generating for myself data, or the modelers are generating data for me that say, okay, here's some samples, give me a yes or no label, and then I can infer whether I can infer something about the set. I mean, there's probably a probabilistic step that says I'm in or I'm not, a la what David was doing. But I can't, I think you asked how can I know that I found all of the set. I mean, I suppose you can't you might hope that you could design somehow the things that you show them in such a way that you insure against some bad things.
If you have a formula that says whether you're in or out, then you can have some sort of guarantee. But if you have a person that says whether you're in and out, you don't have a guarantee. You can't apply the person everywhere. I can apply the formula everywhere, at least in principle.
Yeah, but that's what happens when you partially see some things are in and some things are out, and then you do some modeling to work out what you think is in and what you think is out.
Do you have any further questions? Yeah.
So the Navier-Stokes equation, it has this quadratic nonlinearity. This is the key feature which models transport, momentum transport. And so, of course, it is known in 3 dimensions that the solutions are not necessarily unique. So in 3, this is a 3-dimensional simulation now, so we are in these models away from the 2-dimensional spherical one, which is unique globally. The 3D is not. So yesterday we saw Sullivan's talk in the Bayesian computation, Bayesian numerics. And they have this fruit fly problem, which has the same quadratic nonlinearity in an ODE, which has 2 solutions. It's exactly 2. For the same initial condition. And then they calculate a probability distribution charging the 2 branches with relative probabilities. So how can you be sure that your methodology here, if we drive the system to a bifurcation point, and that your methodology will not miss one of the branches by this, you showed this kind of outlier removal and so on in one of your slides, where you discard extreme temperatures and extreme gradients. But of course, maybe these extreme scenarios, which every now and then happen, are not unphysical, but maybe they are there, and they are just occurring with a low likelihood. But of course, we may drive the whole system, or mankind may drive the whole system exactly to a point where it could flip into such a relatively improbable bad scenario.
Yes.
Say, one example that is discussed is that the Gulf Stream will flip.
Yeah, sure.
It gets here less pleasant than it was so far. Suddenly.
Yeah.
What is your take?
My take is a couple of things. I mean, the first is that the physics package really may be removing a lot of these nonlinearities from the system. So the search for the bifurcation in, for example, the Gulf Stream in any serious coupled model has so far failed. And I was on a project for 3.5 years looking for it. And it seems like there are competing probable explanations for that. So it's not over, but it could be that there's something going on there. But in general, the comment is in some sense that a climate model, a dynamic system like that, has a state vector, and maybe there are 2 solutions, and the sort of classic butterfly equation where you don't know which tractor you're on, and how can you play a sort of UQ calibration game. I think my take is, with the amount of computing power that we have to integrate these models, we can have relatively short runs, and we can't have very many. And I just don't see any hope if we permit ourselves to think, well, what if it's on another attractor? Should we spin the model up for tens of thousands of years to make sure we sample the full initial condition path? It seems to me to be an extraordinarily hard problem. Now, whether we can get something out of more of the models so that you get the integration, you could have the integration every 6 hours, and maybe start to work out some theory as to whether you might jump onto a path or not. But in terms of what they're prepared to give us now, I just can't see any hope. And then maybe that means I shouldn't work on it. I don't know. Don't think I haven't thought that.
That was a candid answer. Thank you.
Okay. So thank you very much, Jim.